Welcome to Ken Matrix Online Academy, your destination for KCSE and IGCSE exam preparation and online coaching. Need assistance? Contact us via WhatsApp at the number shown or email us at mwemaken3@gmail.com. With great honor, I introduce our tutor, Engineer Ken Mwema, who will graciously lead us through this video tutorial. A warm welcome, sir.
Thank you very much for that beautiful introduction. In this particular video tutorial, we are going to talk about Introduction to Differentiation. Differentiation is a subsection of a concept known as calculus, but we are not going to talk about calculus. I will reserve that later in our next video tutorials. Let us go straight to the outline of this particular tutorial. In the first section, we are going to introduce ourselves by first looking at the whole thing differentiation and the meaning of differentiation. We are going to talk about the history of differentiation, a little bit of it, then talk about the real life applications of differentiation. The next section, that is the second part of this tutorial, we are going to talk about curve sketching, and a comprehensive example will be looked at under that section. In the third part of this tutorial, that is kinematics, the study of motion of bodies without looking at force, we are going to see the relationship between displacement, velocity, and time, and relate to and see how differentiation comes into play. In the last section, that is maximum volume, we are going to see how differentiation can be used to find the maximum dimensions of a particular solid. In the example that shall be provided, we are going to focus on a cuboid. So, let us go to the introduction. What is differentiation? Differentiation is a method of computing the rate of change of a function, let's say y, or f of x, with respect to its input x. I'm going to define a function later, the one that has been highlighted in green. I'm going to define what it is later. But there are two ways of denoting a function. We are going to use y instead of f of x because I want to make sure that everybody, even those who are not doing for the O-level, A-level, even for those who are not doing advanced maths, are able to know what is happening. So we are going to use y. So it's just about calculating the rate of change, because quantities change. Quantities normally have a tendency of changing, and they change in some particular laws. So the rate of change is what we say it's differentiation. Without much ado, allow me to give you a few insights into the developments of the differentiation and integration. We're not going to talk about integration here, but the two concepts are somehow related, or better still, we can say they go hand in hand. Isaac Newton, an English mathematician who is also known as one of the key contributors in mechanics, together with his counterpart, a German mathematician, J.W. Leibniz, that is got with Leibniz, they came up with a well-organized concepts of calculus, which is in which differentiation is a subset of. So, and it is under what they did that led to further developments that we are relying on up to date. But now, why are we doing differentiation? Why are we doing? Is it just only for exams? No. There are also some other. There are many applications of differentiation. From now, even my next future video tutorials, I look upon including real-life applications, because it is very important, because many of the teachers overlook this, but it's very important to tell the learner that this is how this particular concept is applied. So we're going to start with the first field in which differentiation is used. In medicine, when trying to find out the cancer cells, the rate of cancer cells, a model can be constructed using differentiation. In engineering, where I am really familiar with many applications, talk about electrical engineering, talk about civil engineering, in structural engineering, where I really specialized in my third year, talk about bending moments diagram, and etc., fluid mechanics, fluid flow, and etc. In history, we want to find out the age of rocks and the age of particular bones, so as to be able to date using maybe carbon-14. A model has to be constructed premised on the rate of change, and that is differentiation with respect to time. In economics, we want to find out the best investment strategy, or rather, we want to make a decision on the best asset to invest on, and that is where calculus comes into play. I will be using the word calculus, but don't need to worry. It's just that is just differentiation. Now, we have already discussed the introductory part, and we are still under introduction. So let us have a quick review on the function, because I said we are going to revisit the meaning of the word function. What is a function? A function in the mathematical context is a set of input with each input relating to the exact output. Now, in simpler terms, a function is just an equation. Think of any equation. Think of a linear equation, think of a quadratic equation, think of a cubic equation, any polynomial equation. Any type of an equation is said to be a function. So now you have understood what a function is. Now let us look at this example of ours here. We have decided to use this example to illustrate what a function is. If a function is equal to y, which is equal to 3x squared plus 4x minus 2, that is a function, then we will say that it is related to some set of input. Now the input is x. Any x value that shall be substituted is what we call an input. Look at the definition, that is the input. Or rather, we can call it independent variable. And this y, whatever that will come out from after substituting the values, the output, this is what we call the output. So we have already known what an input is and what an output is. I'm not going to detail about function because we're not talking about functions. Maybe I'll reserve that later. Now, what is a gradient function? A gradient function is also known as a derivative. Can be called a derivative. It is a change in the function with respect to the change in the independent variable. So when there is a change in this particular function with respect to the independent variable, then we say that is a gradient function. Now let us look at it into detail, and so that we are able to derive a gradient function, or rather a derivative. Now, when you look at that diagram that has been shown, it will be very simple for us to get the gradient of this particular line. But look at this curve. Look at this curve. The gradient of this curve is not uniform. At this point, let's say, the gradient at this point is different from the gradient at this point. The gradient at this point is different from the gradient at this point. Now we want to calculate the rate of change of this curve. Let's say the equation of the curve is given by y is equal to x power n. Now, we are going to talk about differentiation of polynomial. This is a polynomial function. Y is equal to x power n. So if the function y is equal to x power n, the gradient function is just the same as saying dy over dx. So dy dx. Now dy is the change in y, and the dx is the change in x. So dy over dx is equal to n multiplied by x power n minus 1. What we are supposed to do here is just to drop this n here, and then you subtract the power we subtract the power by 1. So we say n minus 1, and then you drop the n there. So n multiplies x. Now let us look at our function. This is the same function that I used when I was defining what a function is, and I was using it as an example. Now, how can we get the gradient function of this particular function? Or rather, how can we differentiate this particular function here? The function is y is equal to 3x squared plus 4x minus 2. So that dy dx is equal to, so you drop this 2 here. So 2 has been dropped there, 2 times 3x. This is, the power should be subtracted by 1, so 2 minus 1. And you see that is plus 4x. We drop 1 there, so that, but 1 times 4 is just 4. So x minus 1. Okay, you see that. And the final answer is dy dx is equal to 6x plus 4. Why 6x plus 4? 3 times 2 is 6. 1 minus 1 is 0. You need to note any number raised to 0 is equal to 1. So 4 times 1 is 4. You can see that this is the final answer. But something to note, the derivative of a constant is equal to 0. And that's why this has not been included in the final answer. We have not included 2. 2 is a constant. Why are we saying it's a constant? Because it is not it's not does not have an x. Now, we have already seen how to do a differentiation. It is time that we look at more comprehensive examples. We are going to start with curve sketching. An example on curve sketching. The equation of a curve is given by y is equal to 2x cubed plus 3x squared. Find the x-intercept of the curve. Now, the x-intercept is the point where the graph, or rather the curve, touches the x-axis. Let's say that's the Cartesian plane, and let's say this is our curve. Now the point where it cuts the x-axis, that point it cuts the x-axis, this is what we refer to as the x-intercept. And at that point always the value of y is 0. So what we are going to do here, we are going to substitute 0. Yeah, we're going to substitute 0. Where we have y, we substitute 0, so that our equation becomes 0 is equal to 2x cubed plus 3x squared. Rearranging the terms, we have minus 2x cubed is equal to 3x squared is equal to 3x squared. Yeah, and then to get the value of x, you're going to do the manipulation, minus 2, then the value of x, divided by minus 2, divided by minus 2, the value of x is equal to negative 1.5. Now, for us to sketch a curve, we have to know where the curve is going to touch the x-axis and where the curve is going to touch the y-axis. Now let us go to the next bit, the y-intercept. This is the y-intercept of the curve. We want to get the y-intercept of the curve. This is the equation of the curve, or rather our function. The input is x is equal to 0, or rather the independent variable, the input. So we are going to substitute 0 everywhere, so that if x is 0, the y-intercept is equal to 0. Now we have already found the points where the curve cuts the x-intercept and the y-intercept respectively. Let us see what is required. Next, determine the stationary points. Determine the stationary points. What is a stationary point? Determine a stationary point. We need to know what a stationary point is. So let me select my pen, and then I draw this. Let's say that is the Cartesian plane. Let me say that is the Cartesian plane. Now, a stationary point, though I have not defined it here, but I can just say it. A stationary point is a point where a curve, or rather a graph, turns around. We can call it a turning point if you like, or you can call it a minimum or a maximum. Now, you look at that point. This point here is what we call a turning point or a stationary point. Turning point or a stationary point. That point that is turning around, where the graph turns around, is what we call a stationary point. we need to know that even before we go to the solutions, I just want us to know that at any turning point, the gradient function is equal to 0. Or we can say the rate of change, there is no rate of change at the stationary point. The rate of change is 0. Let us look at the solutions. The y is equal to 2x cubed plus 3x squared. That is the original equation. But what is the gradient function, or rather the derivative? Dy dx is equal to, now let us see how the differentiation has happened. 3 drops here, you see 3. Let me use a pen. You see where 3 drops? 3 drops there, so that you multiply 3 times 2. And then you have to subtract 1. Like you can see, 3 minus 1 plus 2 also drops there, so that we can multiply with 3. And then you have to subtract 1 there, so that we have 2 times 3. Now you can do the multiplication. 3 times 2 is 6x squared. Why are we saying x squared? X squared because 3 minus 1 is 2, plus 6x because 2 times 3 is 6. X squared, x to the power 2 minus 1 is x, so that's why 6x. And the gradient function of that particular curve is given by 6x squared plus 6x. But remember what I've just said, the gradient function of a stationary point, the gradient function at a point called stationary point is equal to 0. So we are going to equate this with 0. We are going to equate that with 0, like we can see here. Can you see that equation there? So 0 is equal to 6x squared. Now the main idea here is to get the value of x. Now that we have already equated the gradient function with 0, it is now time that to get the value of x. Because stationary point, we are being asked for the coordinates, so we have to get the x coordinate first. So the x is -1. What is next? Like I have said, we need to get a coordinate. So what will help us get the coordinate is bringing back our original solution, our original function. We have said that is the original function, and then after that, this -1 here, substitute it in the original function, substitute the value of x to get the y coordinate. So we are going to come back to the original equation so that we substitute the value of x at the stationary point. Let us see what happens in the solution. So if x is equal to -1, okay, x is equal to -1, the x coordinate is -1. What about the y coordinate? Like I have said, we are going to use the original equation. Please don't confuse the original equation. I know you might be tempted to do the substitution with the gradient function, but it is wrong. You do the substitution with the original function, and then we just plug in the values of y there. The values of x, and then the x coordinate is 1. So this first stationary point, x is equal to this first stationary point, the coordinate is -1 and 1. So you have seen how we get the stationary point. But remember that this equation this equation can also be factored out. How? Sorry. We are talking about this. This gradient function can also be factored out. How? We can say, because it is equal to 0, 0 is equal to x, because x is common, and then we have 6x squared plus 6. Then we close the brackets. Now we can see that the value of x can also be equal to 0. The value of x can also be equal to 0. So in other words, this curve has got two stationary points. But let us inspect the equation. Let us inspect the equation. Let us try to inspect the equation and see the kind of equation it is. Let us go back. Because the highest power is 3, this one is a cubic equation. And in most cases, a cubic equation assumes this kind of a shape. It has got 2 turning points. So after having that rough idea, we can be able to know that this kind of an equation might have 2 stationary points. And one of it has already been found. What about the next? At x is equal to 0, automatically y will be equal to 0 because we have already established that the y-intercept is 0. So the second stationary point is 0, 0. And so let us now go to the next part of the problem. What is the problem asking? For each point in B1 above, determine whether it's a maximum or a minimum. Now, we need to note that we have 3 stationary points, types of stationary points. Number 1, we have a minima. Number 2, we have a maxima. Number 3, we have a point of inflection. Now let us see what kind of turning points these are. We start by writing the original equation and doing the substitution. Now, how are we going to do the substitution? Let me use a different color. Let me choose a different color. I have used red. More. Or let me use green now. Now, we want to see the nature of these stationary points, turning point. I have said it can be minima, maxima, or a point of inflection. So in this, for x, now we are going to guess a value that, focusing on x, we are going to maybe guess a value that is less than -1, and that is -2. Substitute it in the equation, the original equation, not the gradient function, and then you get -4. And you realize that in the left hand side, because when you draw the Cartesian plane, this is the left hand side, we have the negatives. We have the negative in the left hand side. And since we have the negatives in the left hand side, that tells you that from this particular one, it tells you that the nature of that particular curve. Now it is curving how? If I substitute the value of x here, I will get -2 cubed is -8, -8 times 2, -16 plus that. You're going to get this. Okay. Now that means that the value of x is going downwards. It's going downwards. And this is the turning point. There is a turning point. Then when you go to the right hand side, okay, compare with the value of y, the right hand side of this, that is the positives, you realize that we say this is the value of x be 0. Now this is the point, the right hand side, and then you say that the value of x be 0. Substitute 0.5, 0 is 0.5. Let me make that correction. 0.5. Substitute it here, and then you get 0.5. So it gives us a rough idea that it's sloping downwards in that direction, sloping downwards. So this becomes a maxima. It's maximum at that point. It is maximum. So let us look at the next stationary point. This next stationary point, we are also going to do the same substitution. The x is, we are going to say let x be minus 0.5, and then it will give us a 0.5. So we are going to see it's a decrease in nature because it is from minus 0.5 to 0, and this is flat. This is our turning point. And we're also going to do the next substitution in the right hand side. We are going to see there's an increase. There's an increase of y from 1 to 5, and therefore the stationary point of coordinate 0, 0 is a minima. Now, after getting to know the x-intercept, the y-intercept, the points of stationary points, and to determine the nature of the stationary points, now we get to the juicy part, that is the sketching part, the sketching of this particular curve. The question asks, sketch the curve. Now that is our grid. Just know, note that it is not a must for you to use a grid or a scale. We are just sketching. I've decided to use a grid because for the purpose of illustration, and so that you can be able to understand. But if you're taught to sketch, it is not a must for you to use a grid. So we are going to mark the following. I want us to go back to Roman 1, part A, sketch and the curve sketching. What is our x-intercept? Our x-intercept is negative 1.5. Okay, so let us mark it in the graph. Negative 1.5. Here is the point. So I have marked that point. What is our x-intercept? That is y-intercept. Let me check once again. Let me be very sure of what I am doing. So x-intercept is 1.5. Yeah, negative 1.5. What is y-intercept? Y-intercept is 0. So let us mark the 0. Y-intercept is 0. Y-intercept is 0. Now the next thing we are going to mark is the stationary point. The first stationary point is minus 1, 1. So let us look at minus 1, 1, where it is. Minus 1 and 1, here it is. Minus 1, 1. The next stationary point, let us try to see the next, is 0, 0. This one here, 0, 0 is the next stationary point. What are the nature of the turning points? This negative 1, 1 is a maxima, so that means that it is coming this way. So let us connect that. Let's connect that. So it is coming that way, and since 0, 0 is our minima, so it's gonna curve that way. It's gonna curve. Oh, where's my rubber? I want to do something here, but yes. Now, any particular graph must be labeled. So let us label our graph. Let us label. Let me use a different color. I think I really like red. Let me not be biased in this case. Our graph is, let us go to the equation. What's the equation? Y is equal to 2x cubed plus 3x squared. Y is equal to 2x cubed. So y is equal to 2 so y, we have to label the graph. Y is equal to 2x cubed plus 3x squared. So the graph has been labeled. So that is the graph. We have already sketched the graph. Now that we have already seen how a graph can be sketched, let us go to the third part. The third part of this particular tutorial, and that is kinematics. Like I have stated earlier when I was introducing this topic, kinematics is just the study of motion of bodies without considering the force. Kinematics is a branch of mechanics, so we're not going to talk about mechanics, so let us just concentrate on this, and that is the example. The displacement s meters of a moving particle from a point O after t seconds is given by s is equal to t cubed minus 5t squared plus 3t plus 10. Find s when t is equal to 2. You realize now we are not going to use y's and x that we are used to. We are going to use other symbols. Our function here in this case, our function here is s is equal to t cubed minus 5t squared plus 3t plus 10. So that is our function, original function. What we are asked is to find s when t is equal to 2. In other words, we are just going to substitute. This one is simple. We're just going to substitute the value of t, the value of t with the 2. So just a simple substitution, like us can see. S is equal to 2 cubed minus 5, 2 squared plus 3, 2, 3 times 2 plus 10. So where we have t, we use 2 instead, and the displacement is 4 meters. For those students or for those who really do like physics, maybe I can try to give you some little bit of insights. Get to know that displacement is a vector quantity, and displacement is distance, but in a defined direction. So s is displacement, and the units are in meters, 4 meters. Now, Let us now go to the next part of this particular question. That is, determine the velocity of the particle when a t is equal to 5 seconds. This is our gradient, this is our function. We need to know this. And maybe I can try to highlight something here. I can try to talk about something here. Let me use red, my best color. So SVA is a key that I normally use. From this direction, what we do, we are differentiating. From that direction backwards, we are integrating. Now for us, SVA is the key we should use here. Now for us to get a velocity from displacement, we have to differentiate. So V, which is velocity, is equal to ds with respect to t. Our t here is our independent variable, and our s is our original function. So for us to get velocity, we have to differentiate displacement with respect to time. So s, our original function, s is equal to t cubed minus 5t squared plus 3t plus 10. How do we get the derivative? Derivative, as normal, you drop. Let me use a pen now. You drop 3 here. Okay, subtract 1. You drop 2 there. Subtract 1 there. T is the same as t per 1 minus 1. And then you're not going to drop anything because 1 times 3 is just 3. And since 10 is a constant, the derivative is going to be 0, like you can see here. You can see, look at this, look at that, how the differentiation has taken place. So that is it. And now, simplifying it further, you come up with velocity is equal to 3t squared minus 10t plus 3. You realize that whatever we've just found is called a velocity function. The original function is the displacement function. And how do we get velocity from displacement? We do differentiate it. Now we want to get V when t is equal to 5. So we are just going to substitute 5 in the where we have t. We substitute 5. And then solving it further, you come up with 28 meters per second. So this is velocity is speed in a defined direction. Velocity is a vector quantity, and the units are in meters per second. Let's go to the next question. Find the value of t when the particle is momentarily at rest. Let me highlight this word, momentarily at rest. The particle is momentarily at rest. What is the meaning of the word momentarily at rest? Assuming that you have a stone, you are holding a stone on your hand, and then you throw it upwards. That stone, before it falls back downwards, it is going to rest a little bit upwards. And that instantaneous resting is what we call it momentarily at rest. The question can be framed this way also. Find the value of t as when the particle is instantaneously at rest. So at an instant where the particle is just at rest, that instance is what we say the particle is at rest. Now, Maybe now you have understood what we mean by momentarily at rest. When the particle is momentarily at rest, that means it is not in motion. And when the particle is not in motion, then we say the velocity must be equal to 0. The velocity of that particular function must be equal to 0. Any particle that is not in motion, if you are just seated there, the velocity is of yourself is 0. You're not moving. So when it is at rest, the velocity is 0. So now that we've already found the velocity function in the previous computations, we're just going to equate this with the 0. So 0, going to say this equation is equal to 0. Now we want to get t. And you see, it boils down to a quadratic equation. Using the quadratic formula, you get two values of t's. T is equal to 3.610 seconds, or t is equal to negative 0.27770 seconds. So that is how we get t when the particle is momentarily at rest. The last part of this problem is find the time when the velocity of the particle is maximum. Velocity, how is velocity, when is velocity maximum? When is velocity maximum? Velocity is maximum when acceleration is equal to 0. When the acceleration is equal to 0, the velocity is maximum. What is acceleration? For the benefit of the physicists who are watching, acceleration is the rate of change of velocity with the time. So the change in velocity with the time, that is acceleration. Now, how do we get acceleration? Acceleration is a derivative of a velocity function. Now here we are going to differentiate the velocity. We are going to differentiate the velocity so that the dv over dt with respect to t, because t here is the independent variable. I mean, it is the varying factor. So we've already gotten v from our previous computation. It's just a matter of differentiating this now. You see, now it becomes simpler and simpler. The equation originally was bigger, so it is simplified as we get along with our differentiating with our differentiating procedures. So drop this 2 here, 2 minus 1, then this t is the same as t power 1, subtract 1, and then this will be just 0. Okay, like you can see here, 2 times 3, now it simplifies to a is equal to 60 minus 10. So this is acceleration. For you to get acceleration, differentiate the velocity function. So if a is equal to 0, like we have noted here, acceleration is equal to 0, we are going to equate this equation with 0. We are going to equate the equation with 0. Equate it with 0. And then after equating it with 0, you come and get the value of t is equal to 3.333 seconds. That is when the acceleration is maximum. So you need to know that from SVA, displacement, you want to get velocity from displacement, you differentiate. You want to get velocity, the acceleration from velocity, you differentiate. In the next tutorial, I'm going to talk about integration, and the reverse will be true. You are going to see the reverse is true. Now let us go to the last part of this lecture, maximum dimensions and volume. Like I said in the introduction, I'm going to focus on a cuboid. There are many shapes that can be analyzed and that can be modeled using differentiation. But let us look at this simple example. A rectangular box open at the top has a square base. The internal side of the base is x centimeter long, and the total internal surface area of the box is 432 square centimeters. Express in terms of x the internal height of the box. Now, here we have the box. In the question, it has been stated that the box is open at the top. And if it is open at the top, and then we cut the edges. These edges here. That let me use that it's open. We cut these edges here. Cut them. The edges there that are heights. Cut those edges. Then we open. It's going to form something like this diagram. Now, from here to here is h, and that will be reflected here. The base is x, and this is x throughout. That is x, and that is x. So that is the material, the internal dimensions. And the question has stated clearly that the surface area, total surface area of the internal dimension is 432. So take this, add this, and you add this plus this. The total surface area must add up to 432. But then there are four figures here which are the same. Look at this. Look at this one. Let me use a pointer and look at this box here. This has h and x. Look at this one has h and x. Look at this and this. So how many are they? 1, 2, 3, 4. So there are four shapes which are the same, have the same dimensions. So that means the area of all of these four is just the same as 4 times the area of one particular shape. Now what is that shape? Maybe that is a rectangle. Yeah, that is a rectangle. Now the dimension of this is x times h. So for us to get the area of this is just length times width, which is h times x. But there's this one here at the center, which is the base. That's x times x. So the area is x times x because the length is x and the other length is x. So look at it. Total area x times x plus 4x times h. Why are we saying x times h? This is x and then this is h. Why are we multiplying by 4? We are multiplying by 4 because there are 4. 1, 2, 3, 4. We have 4 figures which are alike. So simplifying it further, we have been told that the total area is 432. Simplifying it further, you realize that the total area 432 is equal to x squared plus 4xh. But the question is demanding that we express h in terms of x. Express in terms of x the height. So this height, you're going to make this height the subject of the formula. So let us go to the next slide and look at how we do the manipulations. So from doing the manipulations there, take this to the other side, okay, and then you take further to the other side, you divide by minus 4x, you come up with this, h is equal to 1 or 8 over x minus a quarter x. Now from the indices, maybe we can try to revise some little bit of indices. 1 or 8 over x is the same as 1 over 8x power minus 1. So we just removing this fraction there so that it can be dealt with easily. Minus 0.25x, because 1 over 4 is the same as 0.25. So this is how we can express h in terms of x. Now we have seen how we are supposed to express the height in terms of x. The question will guide us on what to do next. Let us look at what you're supposed to find. The internal volume of the box. Now, from the basic measurement knowledge, we should be able to know that the volume of a cuboid is given by base area times height, or the volume of any particular prism, because a cuboid is a prism, is base area times the height. So the base area, this base area here, where is the base area? Let us go back to the diagram. The base area, this is the base area, x times x times x squared. So the base area is x squared. The base area times the height will give us the volume. But what is the height? We have to, this is x squared, so base area is x squared, here is x squared. We have to substitute the value of h, which contains x's only. We already found the value of h in terms of x, so we are going to replace it with x's. It is very important. So after replacing it with x's, open the bracket, x squared, you come up, it boils down to 108x minus 0.25x cubed. So that is the expression of volume in terms of x. So we want to just use x. Now, you can guess what is coming. Maybe try to guess what is coming. In a few moments, we are going to do what we are supposed to do in this topic, and that is we are going to differentiate that. Let us see how what the question will tell us. Find the value of x for which the volume is maximum. The moment you hear this word maximum, that should tell you that the gradient function is equal to 0. So dv with respect to x. Remember here v is volume. Don't confuse this v with the velocity one. This is volume in this particular example. And this x is the dimension. Okay. So since we have volume, when the volume is maximum, the dv dx is 0. But we have our expression of v. The expression of v is already there. We need to differentiate it. So differentiating, I think you have known how differentiation takes place. It boils down to 108 minus 0.75x squared. And then what is the value of x? The value of x, from that, the value of x is 12 centimeters. You can also get a positive or a negative. So we are not going to use the negative, we are going to use the positive because a dimension cannot be negative. So the value of x is 12 centimeters. Let us look at the next question. Find the maximum internal volume of the box. Now, our original function here, this is the last part. So let me finish up. Let me finish up. This is the last part. So our function here, the function is v is equal to 108x minus 0.25. And we have already found that the value of x is 12 when this v is maximum. So we are going to substitute the value of x in this function of ours. So find the maximum internal volume of the box. So substituting for 12. And then we come up with 864 cubed centimeters. That marks the end of this video tutorial. Thank you for your patience. Let's meet in the next tutorial, and that will be on integration. Thank you.